Hi, I'm Derek. Today I'll talk to you about proof concurrency in our new authenticated dictionary, Aardvark. This was a collaboration that began at Algorand Inc. A cryptocurrency is a payment system that runs on a distributed network of computers called validators. A cryptocurrency maintains a mapping from users' public keys to their balances. Suppose I would like to invest in tulips to become obscenely wealthy. To pay the florist, I sign a transaction with my secret key and then submit it to the validators. Because many users may be submitting transactions at the same time, the validators execute a consensus protocol to determine which transaction to execute next. One issue in this setting is that as many users join the system, the mapping can become very large, which increases storage costs on the validators. We can try to fix this problem by moving this mapping off of the validators onto untrusted third-party machines called archives, which have a lot of storage. One example of an archival service could be a content distribution network, for example. In this design, I first query the archive for my balanced state. And then before I submit my transaction, I attach this balanced state and submit it to the validators. For a transfer, you actually need two balanced states, one for the sender and one for the receiver. For this talk, I'll just focus on a single key transaction to simplify things. So one unfortunate part about this design is that the archives could be malicious and tamper with the state in the mapping and return the wrong result for my balance. To prevent this from happening, we can use a data structure called an authenticated dictionary. One example of an authenticated dictionary could be a Merkle Tree. In this design, we'll have the validators store a small commitment called C that corresponds to the state of the mapping. And to prevent the archives from lying, the validators will require them to return a small proof pi, which can be verified against C and the balanced state. When a transaction is executed, the balanced state will change, so the validators will also need to update C. We can make a couple observations about this system at the high level. First is we want for transactions to have a low end-to-end latency from the perspective of the user, even when many users are submitting transactions at the same time. So we want high throughput. The second observation is that the validators, which are executing a consensus protocol, are often bottlenecked by the amount of available bandwidth in the system. So we can translate these two observations into two corresponding requirements. We want our proofs to both have a low overhead for producing and verifying proofs, and we also want the transmission overhead, the proof size, to be low as well. An advantage of hash-based authenticated dictionaries, such as Merkle trees, is that the computational cost as compared to verifying the digital signature is almost free. You're just computing a bunch of hashes. However, proofs are relatively large here. For instance, with 128 bits of security, proof in a mapping with 1 billion elements is about 1 kilobyte in size, while a transaction could just be 1/10 of that size. An alternative is to use pairing-based authenticated dictionaries, such as with vector commitments. Here, the transmission costs are very cheap, but the computational costs can be quite substantial because these rely on operations on pairing-friendly elliptic curves. So what I'd like to give you is an authenticated dictionary with almost free computational costs and very low transmission costs, but we weren't quite able to do that. We couldn't find a silver bullet. So instead, I'll tell you about how we enable parallelism to manage these high computational costs. To summarize our contributions, we designed Aardvark, an authenticated dictionary with short proofs and short commitments. The insight that allows us to build an authenticated dictionary from vector commitments is that we enable short proofs of an item's non-membership in the dictionary. Our second contribution is that Aardvark provides low latency at high throughput and does this with techniques from transactional concurrency control. In particular, today I'm going to talk about how we version the state in Aardvark to achieve this. I'll give some background first on vector commitments. Let V be a vector of fixed size. The commit operation creates a small commitment C out of V. Let I be an index into V, and let Vi be the element at that index. Open creates a proof pi, and verify takes in an I, a Vi, and a pi, and checks that it was correctly created with respect to some C. There are two additional operations that these vector commitments support, proof update and commit update, which update a proof and a commitment respectively, given an update in the underlying vector. The advantage of the vector commitments that Aardvark uses over Merkle trees is that the proofs are very small. They're only 48 bytes large. Unfortunately, these operations are much slower. For instance, for vectors with 1,000 elements, the open operation could be more than 4 orders of magnitude slower than the corresponding operation in a Merkle tree. I'm going to go into a little more detail as to why these high computational costs are such a problem in this setting. Suppose the validators hold a commitment C that corresponds to a mapping from K1 to V1 and K2 to V2. Suppose we have 2 clients that issue simultaneous queries to the archive for K1 and K2 respectively, and the archives respond to this query by using the open operation to produce the proofs. When the validators execute the transaction from the first user, the commitment will update to C prime using the commit update operation. And the problem is that the second client will have an old proof against the commitment C. It can't be verified against C prime. So with the interface I gave you, one thought is maybe we can update pi so that we can verify it against the new C prime. The problem with this approach is that the work required to implement such a policy scales quadratically with the number of outstanding transactions in the system, and this can create a bottleneck for the system-wide throughput. In particular, anytime a transaction is executed, all the proofs in the system become instantly outdated, and these proofs must be updated before their corresponding transactions can execute. Specifically, we can consider 3 different options. We can have the archive rerun open when the proof is outdated, or the client or validator run proof update. If the archive reruns open, then the client needs to send a new request to the archive on every update to the state, and this will add many additional round trips. If it's the client's job to maintain the freshness of the proof, then the clients need to hear all the updates, and this can be very expensive for a client that might be resource constrained. Finally, suppose that the validator's job is to execute proof update. So in this system, consider that at the validator, we're going to have a backlog of transactions basically build up. And as this backlog grows, the work required to process any additional transaction also grows. This creates a positive feedback loop, because all of the proofs must be updated, and this can lead to congestion collapse at the validators. The fundamental problem here is that the stale proofs force serialization of the proof-related operations, and this slows the system down. Our insight is that we can cache old state to maximize the opportunities for the system to take advantage of parallelism. In particular, Aardvark adds to every commitment and every proof a version number. When the validators execute the first client's transaction, not only do they compute the new commitment C prime at version 2, but they also retain the old commitment C at version 1. And this allows them to continue to verify the stale proof held by the second client. One additional case we must consider is if both transactions share a key. And in order to handle this case, we require the validators to hold all recent updates to keys and values for some time. There are some additional details we must handle to integrate this versioning scheme into Aardvark. In particular, this scheme interacts non-trivially with the non-membership proofs that I didn't describe. If a proof is created concurrently with the insertion of a new key or a deletion of an old key, then Aardvark has to correctly handle this case. And we refer you to the paper for more details here. For our evaluation, we integrated Aardvark into the Algorand cryptocurrency. We saw that storage costs were reduced by about 3 orders of magnitude, and proofs were 100 to 200 bytes in size. And we wanted to empirically evaluate how much does the system slow down when we integrate Aardvark into Algorand. This is a pretty complicated question because, as you saw, there are many parts to the moving parts in the system. And so for this talk, I'll focus on the processing costs at the validators. We evaluated Aardvark on an Amazon EC2 instance. We spread out 100,000 operations of various kinds over 10 blocks, and we executed them on a dictionary with 1 million keys. We found that the processing overhead for a single 1 megabyte block ranged from 34 to 68 seconds, which is kind of a lot. But we also increased the number of cores from 1 to 32 and found that we got about an order of magnitude of speedup. The reason the speedup is imperfect is because not all of the commit update operations are perfectly parallelized in our prototype. I'll talk a little bit now about related work other than Merkle trees. So EDRACs, hyperproofs, which you saw yesterday, and other vector-based commitment schemes also have pretty high costs for computing and verifying proofs. And we believe that Aardvark's versioning mechanism can help us manage these proofs in these other systems. The session chair will be upset at me if I don't mention zero knowledge. ZK rollups and ZK snarks are another way to reduce storage costs. And here the verification costs are excellent. The process, like creating the verification of proofs and transmission of proofs has almost a constant cost and is extremely efficient. The drawback is that proof creation is relatively slow. It's about an order of magnitude slower per transaction than vector commitments. And also because to get these good verification costs, batching is required. So batching will increase the latency for a transaction. In conclusion, I described today Aardvark, an authenticated dictionary with short proofs and short commitments. Aardvark achieves low latency at a high level of throughput by using techniques from transactional concurrency control. Thank you very much for listening to my talk, and I'm happy to take any questions.